Hello, welcome back to Decaf-Math. Hello. If you are new and just joining, welcome. And if you haven't done so already, I encourage you to introduce yourself and let me know what you think about math. And don't worry, I won't be offended if you hate it. If you hate it or find it boring. Either way, I hope that you find this relaxing and helpful. So today I wanted to start going over the idea of finding limits at infinity and negative infinity. I'll probably make this like a little mini series just because I don't want to have the video go super long and get to important examples like at the end or anything. So feel free to just skip around to whatever you find helpful. This was requested by a lovely new viewer, so I hope that you find this especially helpful. Hello. And today I wanted to focus on finding limits of polynomials and constant functions. So this will allow us to not rush and we can really focus on getting a solid understanding. But if you already feel like you understand this, feel free to skip along. I'll add this all to a playlist so you can just jump around to whatever you find helpful or relaxing. So, and also for those of you who liked the trig videos, keep an eye out. I will keep making those as well, so don't worry. So we are going to do, let's see, limit of polynomials, I said. So limit of 5x squared minus 3x plus 1. Remember, as x approaches infinity. So remember, we're talking about polynomials which have this form. You might have seen it with like a 1 and everything might be like backwards for you, but in general, we're just talking about a bunch of coefficients with x raised to powers, right? So x to the 1 is x, but x2 plus a n x to the n, right? So a bunch of coefficients times x to the power of a whole number. So something as long as n is greater or equal to 0. If it is equal to 0, remember we'll have a constant function, but otherwise we have 1 for a linear function, or 2 for quadratics, or 3, 4, 5 for higher power polynomials, right? So we're going to talk about how to find limits of these as x approaches infinity. So remember that when we find limits, we are talking about what value y approaches, if anything. So that is the basic idea. As x approaches something, what does y approach, if anything? So remember that we have to have a strong understanding about what functions are and how they work to do this, because remember that on the xy coordinate plane, x's are independent variable. Independent. So it doesn't matter what we input, but our y is dependent on the input that we give it. So our function tells us what to do with that input value. So if I give you a value, you know that this function tells me I square it times 5 minus 3 times that number plus 1. And then if I graph all those points, which we put as ordered pairs, we get a picture of something. So this is a quadratic because of the 2, but just here's a random other picture of a different function of some sort with no values, but just a general idea. So when we're talking about limits, we want to say, okay, as x approaches a certain value, or in this case infinity, it gets infinitely large, what happens to the y values? It might approach something, it might not. So the limit doesn't necessarily have to exist, but we can calculate some limits. So when I first learned limits, I was very confused because I'm a very visual learner. I understood it just like how to calculate and just like from rules, that was fine, but to really understand, like especially when you talk about the epsilon and delta definition of limits, seeing this picture didn't always help me. But what might help is to actually make a table at first. Like let's say you're trying to find the limit of 1 over x as x approaches infinity, something like this, and I might actually make a video on this too. And And this is not the graph of that, by the way, but it might help to see, okay, I'm going to pick some x values that get very, very large. So I'll start something like this, maybe jump to 10, and then, 100, and then just get really, really large and see what happens, really, really big, and then find the y values, which would be 1 over these x values. So to get you started, like 1 over 1 is 1, 1 over 2, 1 over 5. You might want to make these decimals, right? But then you're really focusing on what happens to these y values. So remember, if you're not used to like reading off a graph, because when you're plotting these points, it's x, which is the horizontal direction, comma y, the vertical up and down, right? So you're just kind of reading off of it to see what the y values approach. Then once I kind of did some tables like this, it helped me a whole bunch and I could read off the graph much better. So that might be a little tip for you, but here we have some general patterns and lines of thinking that can really help in solving these types of limits. So when we're doing polynomials, it might be tempting, especially if you're coming straight off of a unit of finding limits as x approaches a specific value, it might be tempting to try this. And if you already know this, you might cringe. But it might be tempting to think, okay, I'm just going to plug in infinity for x. So 5 times infinity squared minus 3 times infinity plus 1. Oh, something really big squared must be something really, really big. So this is infinity minus, 3 times infinity is really big. So infinity plus 1. Oh, okay, so something really big minus something really big, this must be 0. So the limit is 1. Okay, so if you are not tempted to do this, then don't be tempted now. I'm trying to make this really not appealing. Don't do this. But it totally makes sense why you would, because one of the methods for finding limits as x approaches a value is to just plug in that number here. So instead, what we're going to focus on is which part of this has the most weight. What matters the most, okay? So you kind of can think of it as like the rate in which it changes, or which one has the highest effect. You could make a table for some values here and see what's going on, but we can sort of logically come up with the general rule. So if x is really, really big, so remember, infinity is not a number, and that's just kind of the main difference with finding limits as x approaches infinity and x approaches a specific number. But infinity is not a number, but we can think about 1 with a bazillion, gazillion, trillion zeros after it. And if we plug that in, we have 5 times a really large number squared. When you're thinking on that scale, and then you're like, oh, plus 1? This plus 1 is not going to mean anything, right? It's not going to do anything. Who cares if we're talking about 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 1. Who cares, right? So on that scale, this 1 doesn't really matter. So finding limits at infinity is actually so cool. It's like changing your perspective. When we're talking about x being that big, this isn't going to matter, and neither is this negative 3x. Why? Because let's think about if x is, let's just say 10, which is not super, 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 super big, right? Already with something not infinitely big, we're just talking 10, we're comparing 500 and then minus 30 and then plus 1, right? So this is like negligible. I mean, it's not really negligible just yet, but still 1 compared to 500 and 30 compared to 500. We're talking about just 10. Now imagine if we're talking about like 1,000. Like 1,000, so that's 10 cubed, right? So 10 cubed squared is like a million. So we're talking about 5 million compared to 3,000, right? And then plus 1. So 5 million, 3,000, and 1 minus 3,000 and 1. These are negligible, especially when x gets super, 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 super big. So the only thing that matters is the thing, there's our leading term. our leading term. So that's going to be the term that has the highest degree, the highest power, has the most power, right? So this 5x squared is the greatest contribution and the rest falls away, just falls away. So now we're really talking about the limit of 5x squared as x approaches infinity. Well, now you can do the thinking of, okay, a really big number squared is just infinitely big, and then times 5 is still infinitely big. So this limit is infinity. It's infinity, okay? Okay, so let's try limit of the same exact polynomial, but as x approaches negative infinity. Negative infinity. So we can follow the same line of thinking with this negative infinity. When we do that squared, a negative number squared is positive, so this will be huge, 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 huge. And then negative 3 times a big number. A big negative number is going to be a huge also, so you're going to be plus and then plus 1. So this is going to be infinitely big. So I mean, in this case it's a little bit different. You're gonna have to think about your different questions, but even if this were, even if this were plus and you had huge minus huge plus 1, it does not cancel, okay? So again, you would still focus on your leading term, because relative to everything else, this one has the most weight, and everything else just kind of goes away. It goes away, okay? But the important thing when it comes to negative infinity, so for positive infinity, you can just follow this reasoning and it will always be positive infinity. But for negative infinity, sometimes it'll be negative infinity and sometimes it will be positive infinity. Why is that? Well, it depends on if this leading term is even or odd. So if you have learned this already, if you've maybe done this in pre-calc or the beginning of calc, when you study polynomials, when you have an even degree, you know that the end behavior, when you study the end behavior, usually you haven't learned this in the context of limits yet, but you do know something about the fact that there might be stuff that goes on in between when you study the zeros, maybe the multiplicity, but then when you're trying to study the graphs, you know that if it's even, you know something about the end behavior. They're going in the same direction, right? So when x gets really, really small, you know that it's either going to go up like this to infinity, both of them, or negative downwards, but they're both going to go the same direction, as opposed to an odd function. So let's say this were 6x cubed, you know that on one side it's going to go up and the other side is going to go down, or maybe the other way, like this. And there might again be stuff that happens in between, something like that, but you know what I mean? So the end behavior is actually what we're talking about with the limits to infinity and negative infinity. So in this case, if I'm looking at the leading term, 5x squared has the biggest contribution to whatever our limit actually is, the biggest weight, the biggest power. It is even. So if you think about 5 times a really, 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 really negative number, and then you square that, that's going to be positive, because, and you can also think of it as just negative, negative 2 to the power of 4 is a positive number. You can think of that as like negative 1 to the power 4 times 2 to the power 4. So negative 1 to the power of an even number is positive. So this is going to be positive infinity. That's it. That's it. You got it. So same for any polynomials. You can just think about which one is the leading term, which is the highest power, which is going to have the most weight when we're talking about that big of a scale, right? On the infinity scale and the negative infinity scale. And then we just, for negative infinity, x approaching negative infinity, we just look at if it is even or odd. So you can do any kind of polynomial this way, but again, remember this is what a polynomial is. So we're only talking about this form, no square roots, no fractions, and stuff like that, okay? So that's just the first type. And then of course, if we do constant functions, So the limit of the square root of 17 as x approaches infinity, and the limit of the square root, or let's see, how about e, of x approaching negative infinity. What are these two? So these might be so simple, but they can be kind of tricky. But remember that f of x, if f of x is square root of 17, it is a constant function. Or e, it's a constant function. So what does that look like? What does y equal the square root of 17 look like? Take some time to think about that, and you will find that it is actually just a horizontal line. It's just constant. No matter what x you have, your y is constant. So this will be at square root of 17, and this will be at e. But you know that no matter what x value you have, y is e. What x value you have, y is square root of 17. So if x is super big, does this approach anything? Well, y is still square root of 17. So this limit is still square root of 17. Same for x approaching negative infinity. This way is still going to be e. Pretty bland, right? Pretty bland. Very vanilla of a problem. But actually, no, vanilla is the best. I would like to see these on a test. That would be nice. But I wanted to point it out just in case this seemed kind of so oddly simple and if you're doubting yourself. But that's it. So we've already done polynomials now into positive infinity, negative infinity, and constant functions. So next we will do rational, finding limits as x approaches infinity and negative infinity for rational functions, and specifically in the form of some kind of numerator divided by a denominator. Okay, and we might have two polynomials like that. Okay, well, I hope this helps, and I'll see you around. Bye-bye.